Today I want to talk about one last application of, all of these kinds of things that we've been talking about under the guise of Lagrange multipliers specifically, but really what these are optimization kinds of problems. And so I want to just talk about one last optimization problem. And the reason why I did this is because at least Matt and Sam have or are currently enrolled in statistics classes, I guess I should say. And I mean, all of you guys are going to run across this kind of idea at some point if you haven't already. I'm sure you all have already, whether or not you realized it. And the idea that I want to talk about is this idea from statistics of lines of best fit, which are typically called linear regression problems. And, what's the idea here? So the setup is that you're given some sort of data, right? So given a collection of data, and your data, for simplicity here, we'll just use x, y coordinates, right? So we won't make it super complicated for this. It'll be complicated enough just with x and y coordinates. So, suppose you've got one data point, x1, y1, another one, x2, y2, and so on, up through some final observed bit of data, xn, yn. And, the idea is that you could plot these things in the plane, and you could just look at, here's, let's say this dot right there is your first data point, and your second data point, your third data point, and so on, right? And you've got a bunch of these things scattered throughout the plane for different values of x and different values of y. And the idea is that, if you sort of stood far enough back and squinted hard enough at this thing, it might look like a generally linear kind of relationship. And so the idea behind a line of best fit is that there's some rigorous way of figuring out some equation of a line that should, in some sense, be a best fit for this data. And number one, I want to make rigorous this idea of best fit. What does it mean to actually be the best fit for this data? And then once we have an idea for what the best fit actually means, and what I drew here is probably not the line of best fit, by the way, but that's all right. Once we have an idea for what the line of best fit, or rather what the idea of being a best fit means, then we'll actually go through the details of rigorously figuring out how to calculate this thing. All right, so the idea is that this is some line which we can give, our standard like algebra 2 pre-calc kind of notation for y equals mx plus b is the equation of this line. And what we want to do is we want to find m and b. Those are the two unknowns that really completely determine this equation of this line. Right? M and b are the two things that determine what that line is. Find the slope and find the y-intercept such that the error between the actual observed data, which are those x1, y1s, x2, y2s, and so on. So the error between the data and the line is minimized. This is what it means to be best fit in some sense. All right, so we want to minimize error. This is the idea. All right, and you can, just looking at this thing, you can see that there's a non-trivial amount of error going on. Right, so if I draw just how far away from the the actual line this thing is in blue, right, the actual data points have some non-trivial distances away from the line. And if you were to add up all of these lengths of these blue segments, then you would have some sense of how far away the actual data is from the red line. All right, and you can calculate those lengths, just using the fact that you know what the equation of the line is. It's mx plus b, and the idea is that as you vary m and as you vary b, you will change the lengths of those blue lines. All right, so the idea is to figure out which values of m and which values of b will minimize the error. Okay, so this leads me to another very important point, which is that what the heck do we mean by error? All right, so the word error has many, 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 many meanings. Even in math, they have many meanings. What are we talking about here? We've got this idea of error, which is just a straight line distance that I drew a second ago. You could define error instead by being relative to these x coordinates, right? This is like x1 was that data point, x2 was relative to that data point, x3 was relative to that data point, x4, x5, x6. Right, and all I'm doing is just looking at my data points that I drew on the x and y axes here, and I'm just tracing them down to the x-axis, right? So x1 is like that. That's not a very straight dotted line there at all, but right, x1's the approximate x-coordinate of that data point that I drew. All right, so you could also define error in this sense, right? You could look and say, okay, at x2, for instance, I want to find the values of m and b that will define this line that make this distance. If I could draw here, that would be helpful. There we go. This distance, right, that little blue distance, the shortest possible. All right, or at x3, I want to minimize that distance, right? This vertical error, in a sense. At x4, I want to minimize that little vertical error. At x5, I want to minimize that error. At x6, I want to minimize that error, and so on and so forth. All right, so this is another way that you could define the error. It could be these little vertical deviations. So, what is the right kind of error to consider? That's a question you should be asking yourself. And the short answer is that there is no right error in any given setting. There's merits and there's downfalls to using all sorts of different kinds. And this is one of the things that makes statistics so darn hard. And data analysis in general. How are you going to define your error, and what does it mean to minimize one error versus minimizing another error? What are the merits of doing one versus the other? Right? These are all incredibly complicated questions. So, the first thing I want to do is make rigorous what I mean when I say error, and then we will build up the theory of what we're going to do from there. So the easiest way to do this is what I currently have drawn. That's to look at the vertical deviations. Now, the reason why this is easier is that you're sort of minimizing the amount of stuff that changes from one point to the next. So what I mean by that is that, in comparing, let's look at one of these specifically. If we look at, let's say, this one right here, right? We're comparing, which one would this be? This would be x3, y3. So the length of that blue line there is the distance from the point x3, y3 to the line y equals mx plus b. All right, and the reason why it's nice to consider just the vertical deviation there is that this distance, I'll write it down here, this distance from x3, y3, oh, I'm sorry, not a fraction, vector is what I'm trying to write, y3 to the line, which is going to be given by x and mx plus b, since y is equal to mx plus b. Now here's the really important part. In looking only at that vertical distance, that blue vertical distance there, that means that I know what x is, right? I know exactly what x is there. It's x3 again. The only thing that's changed is the vertical displacement, which is, that's a 3 down there, which is given by mx3 plus b. All right, so this is going to make my my error a lot easier to calculate, because this is just going to look like, what do I mean by distance? First of all, that's a question. For the sake of this, I am going to mean the regular Euclidean distance, right? So the square root of the sum of the squares. So what I mean here is the square root of x3 minus x3 squared plus the difference y3 minus mx3 plus b squared. All right, and this is nice because, of course, x3 minus x3 is 0. So I've got the square root of y3 minus mx3 plus b quantity squared under a square root. And remember, we looked at this in class, not, of course, in this exact setup, because this is brand new to us, but we looked at another situation where we ended up with a square root of something squared, if you remember that. I think we were looking at cross-sections of, not y, but z equals the square root of x squared plus y squared. Right, we were trying to figure out what that surface was. And in looking at the cross-section when x or y is equal to 0, we end up with z equals the square root of, say, x squared, which ends up giving us the absolute value of x. And this thing ended up being a cone. Right, so we've already seen what happens in this case, right? We've got the square root of a quantity squared, and so this just turns into absolute value y3 minus mx3 plus b, like that. Now, this would be your error just between the third data point and the line, right? So your remember, what we're trying to do here is minimize the error between all of the data and the line. Not just one data point, but the entire data set and the line. So what this means is that we're going to have a different amount of error, which we've already seen, right? There's a different little length of blue line there for every single data point. So we're going to have a different error for every single data point relative to this equation of the line that we have. So what we need to do is figure out, and I think Did I mention this yet? No. What we need to do is figure out the way that we can minimize all of those errors at the same time. So what we're going to do is we're going to define a cumulative error function. All right, so our error function is going to be the cumulative error between our line and the data set. So what that's going to be is it's just going to look exactly like this absolute value thing going on there, except we're going to have one for every single data point. So what this is going to look like is, you know, y1 minus mx1 plus b plus the same thing for you know, x2 and y2 plus all the way up to yn minus mxn plus b. And this is going to add up every single one of our errors between every one of our individual data points and the line that we're trying to find. Now, we would want to minimize this. And this is where we are going to run into a significant problem. All right, if we want to minimize this thing, we're going to need to take derivatives, right? We know how to minimize things in general using Lagrange, and this is not, I want to make this very clear, this is not a classical Lagrange setup for a minimization problem. And I want you to think about, what are we missing, right? If this were going to be a Lagrange problem, we would need something very specific. Along with the function we're trying to minimize, we would need something else. And I want you to think about what we're missing there. So let me just say, you know, without giving the game away, this is not a classical Lagrange problem. But it is still a minimization problem, and we do know how to minimize things in a sense. Right? If you think about what happens in Lagrange, you're asking, when is the gradient of f parallel to the gradient of whatever your constraint is? Well, if you don't have a constraint, then what you're really asking for is, where is the gradient of f equal to 0? All right, this is going to be where your function is, all the candidate points for where your function is going to be minimized or maximized. So this leads us to our problem, and I guess I should make this a gradient of e instead of a gradient of f, since I call our function e. This leads us to a serious problem. If we want to calculate the gradient of e, we are going to have to differentiate a bunch of absolute value functions. And if you remember what goes on with absolute value functions, right, if I were to draw the absolute value of x, right, the graph of the absolute value of x here, it looks like that when x is positive, and it looks like that when x is negative. All right, so this is y equals absolute x. And that is a big problem because that is not differentiable at the origin. All right, so this thing is not differentiable at the origin. And that is a serious problem. As far as calculating a gradient goes, that's a big problem for us. So what we're going to do instead is take the exact same idea that we have here and adapt it a little bit. All right, so I'm just going to scroll back up to what we did here. And what we're going to do is just be, I don't know, a little bit clever, I guess. What we're going to do is the exact same thing I just said here. And let me get a new color for this. What we're going to do is the exact same thing I just said we're going to do up here, except instead of looking at the regular old distance from our data set to our line, we're instead going to look at it squared. All right, so if I throw a square on that right there, well, that's going to cancel out the square root. And if I cancel out the square root, what I'm going to be left with is a quantity squared. All right, and if I get rid of that expression there, then I'm left with this. Right, in analyzing the distance from our data set to our line squared, what we end up with is a quadratic kind of thing, as opposed to an absolute value kind of thing. So what that's going to do for us is down here in our error function, it's going to leave us with a quadratic error function. And on the surface of things, that might make it seem like it's going to be harder, right? Because quadratics are not as nice as straight lines. However, it's actually going to be a lot nicer because quadratics are differentiable everywhere. We don't run into this problem of non-differentiability. All right, so what we're going to end up with for our error function here is instead of sums of absolute values, that should be a yi, shouldn't it? We instead have, y1 minus mx1 plus b squared, and that's quadratic, and that's beautiful for us as far as differentiability is concerned. Yn minus mxn plus b squared. All right, so we want to minimize this function e. And now we can do this, right? We can absolutely consider the gradient of this thing because it is a quadratic now. We don't run into the same problem that we had just a second ago when we had absolute values, right? All of this, all of that problem that we had a second ago is now alleviated. All right, so let me jump onto the next page here. This is a very famous problem. It's called the least squares linear regression problem. And least squares comes from the fact that we're not minimizing distances, we're minimizing distance squared. All right, so your least squares notion is expressly written out right here. You're minimizing not distances, but distances squared. All right, and what that buys you is differentiability. All right, it gives you differentiability everywhere. So this is what I was trying to say earlier when I said that there are a lot of different ways of measuring errors. This is not the classical way of measuring error in a sense, right? This is not just a straight line distance. And if I go back a page, it's not even the straight line distance from the data set to the line, right? It's not the closest possible point from the data set to the line. The closest possible point would be, somewhere around there. And we're looking instead at just vertical variation, right? So we're taking some serious liberties here with how we're measuring this error. At least it seems like we're taking liberties. Maybe everything's fine, right? And as long as you're very clear about how you're measuring error, everything is fine in a sense. This is why having an ability to read and understand statistics is important. All right, so this is the function that we want to minimize, the so-called cumulative squared error function. And phrasing it as a optimization problem, this is our objective function. It's e, which is the sum from 1 to n of our squared errors. And take a second. Think about what should actually go inside of the parentheses here that I have open, right? What is e a function of? Take a second and think about that. All right, so hopefully you see what's happening here. The data that we're handed is fixed, right? This is data that you observe, or it's handed to you, right? You've got a spreadsheet of data. And so the yi's and the xi's are fixed, right? These are, that kind of looks like an x sub dot dot or an x sub colon, but that's supposed to be an xi. These are, these are numbers that are just handed to you. And the only things that are actually changing in this problem, right, the things that we have to figure out are the slope and the y-intercept of our line. Right, so those are the variables that e depends on. And so the idea here is that we want to minimize this this objective function. So what we really want to do is we want to solve gradient of E equal to 0. And again, if you think about it for a little bit, this is exactly what should happen in Lagrange if you don't have a constraint. Right? We don't have a constraint here. So what we're saying is that, normally in Lagrange, we should have some gradient of g over there, but we might as well take g to be the function that's constantly 0, since we don't have a constraint. And the derivative, right, the gradient of a function that's constantly 0 would be 0 itself. All right, so this is what we're looking at. We want to solve where is the gradient of our error function exactly equal to 0. All right, so I will take care of this in the next installment of this video. Before you start that video, I want you to take a second and try to calculate the gradient of E. All right, go ahead and spend a few minutes on this. It might take a little bit because there's a lot of symbols flying around in the definition of our error function. So take a few minutes, try to write out the gradient of E. And remember that this should be the partial of E with respect to M, partial of E with respect to B. All right, so it's only a two-dimensional vector, even though there's a ton of data flying around in the definition of E itself. When all is said and done, this should only be a two-dimensional vector. Okay, so take a little while, work on that before you start the next video.